Hello and welcome back to GEO 572 Advanced Hydrogeology. Today we're going to keep talking about reactive transport, about groundwater transport, but we're going to move from solutes that are just sort of moving only because of groundwater flow and not reacting or being affected by interactions with sediment. And these solutes we call conservative. That means that they don't have reactions. Today we're going to start talking about non-conservative transport or reactive transport and start thinking about how different kinds of reactions might affect the way a solute moves through the subsurface. So let's go ahead and get started. So let's start off with by thinking about our good old REV, representative elementary volume of porous media. So we've got some cube of porous media here. My drawing skills are not on as well as usual today. So I'm going to erase this and start it again by gum. This is an important thing, the REV. It's not something to be lightly drawn. Okay, so we got our REV. It has dimensions delta X, delta Y, delta Z. And we're going to draw in some sediment grains here. Because our REV is an REV of porous media. All right, so we've got sediment grains here. And when we think about reactive transport, it's important for us to think about the phases that we have in our porous media. So here will be fully saturated, so all of our pore space is full of water, right? And so we have two sort of reservoirs in our porous media. We've got water, all right? And we've got sediment or rock, all right? And so we have two reservoirs where solute can reside, all right? And we can consider reactions that include both of these reservoirs in this case. So our first reservoir, and the one that we're generally most interested in, is the water reservoir. And or aqueous. We're going to use aqueous because we're going to be doing chemistry. All right, and this is the mass, all right, or the solute that's in the aqueous phase or in the water. All right, and the sort of the mass, the aqueous mass in our reservoir of a solute is given to us as the concentration in the aqueous phase, C aqueous, times the volume of water over the volume total. All right. So the total, this guy right here, is porosity. All right. So the mass in our REV of solute in the dissolve phase is C aqueous times N. So similarly, in all of our equations, we're often interested in the change in aqueous mass with time. So the change in mass with time is the porosity times the change in aqueous mass, dC aqueous dt, with time. So this is the change in mass with time. Okay. So that's our first reservoir. All right. Now this is the mass of little bits of solute that are dissolved in the water, right? And up till now we've just considered these solutes and they're just drifting along with the groundwater velocity, and we say that we don't know the true velocity, and that they also move around um, due to random molecular motion. So they spread out a bit, but so far they've only moved due to these like molecular motions and differences in the velocity of groundwater. All right, so we're gonna talk our first, I guess, interaction that we're gonna consider is the fact that, maybe these solutes might stick. All right, attach themselves to the surface, right? And solutes that attach themselves to the surface, we call those that sorption. All right, and this is solutes that stick to mineral surface. And they're not chemically bound, but they are attracted and they are held there. All right. And so there's another reservoir here where solutes can reside. And when they're stuck to these mineral grains, all right, they're not available to move with the fluid velocity, right? They're stuck there. Whereas these ones in the aqueous phase, they can move along with the fluid flow. All right, so our second reservoir is the sorped reservoir. And so some important things about the sorped reservoir that we talked about. That it's technically still dissolved, but it's stuck. All right, so it's not mobile. So it's not chemically bound to the mineral surface, but it's no longer mobile. So it's let's do this A. It's still dissolved, all right? But it's electrically bound or attracted. It's electrically bound to the mineral surface, all right? And if we were to sort of zoom in on our mineral surface, there's a whole, so here, let me redraw this, let's say that we've got a mineral grain here. All right, and it has areas where there's, say, positive charges due to the mineral lattice structure. And we've got an ion, a dissolved ion with a negative charge, all right? And there's an attraction between these two charges, all right? And there's a pretty large field of study that is surface liquid interaction, because all minerals, most minerals, they'll have some kind of a surface charge because the electrons aren't shared equally between all the atoms within the crystal lattice. And so certain portions of the crystal lattice have a charge, and so they'll be charged. And then remember, we've got this water molecule that's that goes like this, and it's got a positive and it's got a negative charge. And so you'll line up like you'll line up sort of water atoms on this surface, and you'll get solute sort of, then the water atoms now have a net positive charge, so solute will kind of also be attracted to the water. And so there's always, if you have a charged particle, there's often absorption and an attraction between these two, depending upon the surface charge, and the role of water, competition with other ions. All right. So so sorption is driven by these. Electrostatic interactions. And they can get really complicated, all right? And, a big portion of a aqueous geochemistry class is thinking about how the different ways you might describe this process. We, for our purposes today, are only going to consider the most elementary of these models of how you might try to mathematically simulate or describe this interaction, all right? And so we're going to consider what we call linear sorption. All right, and the main idea with linear sorption is that the concentration of sorped solutes, all right? So the concentration of these guys that are sorped or stuck onto the mineral surface is linearly proportional to the concentration in the water. All right, so the basic idea here is that there's sort of an infinite amount of sites here that the mineral has, and if we have more solute, then we've got more of these things moving around, and there's going to be more of them stuck onto the ball. And that essentially, if we have this kind of relationship, that the ones getting stuck on and the ones leaving are in equilibrium. And so we write it this way, K D. So the amount of sorbed concentration is equal to the aqueous concentration and related by this KD, which is called the sorption coefficient. So KD is the sorption coefficient. C sorp is the concentration. Of sorped solute. All right, and this unit here is, say, oftentimes reported as milligrams, all right, of solute per kilogram of sediment. All right, so if I took, a kilogram of this sediment and I extracted all the sorbed concentration and weighed it, that's what I would get. All right. And C aqueous here now is going to be milligrams of solute per liter of water. All right, so I've changed my concentration here from molal to a milligram per liter. All right, it's a mass, and you can do that conversion really easily just by multiplying by the molar mass. Okay, so let's think about what the units of KD are. So we've got, if I do a unit analysis here, I've got milligrams solute per kilogram of sediment, right? And this is milligrams of solute per liter water, all right? And for these two sides that have the same units, this needs to be liters per water, and this needs to be kilograms sediment. So C aqueous has this unit of liters per water, kilograms sediment. It's a weird unit, but it's the linear relationship between the aqueous concentration and the sorption and the sorbed concentration. All right. So this is this often gets called a linear sorption isotherm. All right. And basically it just means that if we were to plot here's C aqueous and here's C sorbed, all right, our line would look like a straight line. All right, so the more we have dissolved in the water, the more we're going to have sorbed, and the slope of this line is KD. All right. Okay, simple model. Let's think about how that affects our transport. So let's consider one-dimensional advection dispersion with constant velocity So dc dt is equal to our mechanical or hydrodynamic dispersion coefficient, dH times the curvature in concentration gradient minus fluid velocity in the x direction times the gradient in concentration. All right, so dispersion, advection. And now we're going to add another term, all right, plus R, where R are reactions. And these reactions, like for example, we're going to first put in sorption here. And basically what we can think of is these reactions are a source or sink of mass, of solute mass, all right? And so they're a source or sink in our REB. We could think of them as, you know, either something that's pulling mass out or something that's adding solute mass, all right? So they're just a part of our mass balance. And they're it's a place where we can put or consider reactions that might take mass out. So here, from now on, when I write C, I'm implying C aqueous. All right. And so so upper script C means aqueous. All right. Okay. So I want to conserve mass in the aqueous phase, and I want to consider, so for sorption, I need to write a conservation of mass such that, you know, the change in concentration with time in the aqueous phase is equal to negative concentration change in the sediment phase. All right, so all I'm saying here is that if I pull concentration, if I pull solute out of solution to be sorbed, all right, then it changes the concentration in the aqueous phase by making it less, and it increases the concentration on the sorbed phase. All right, so the concentration change in the aqueous phase is equal to the opposite change in the sediment phase. All right, and now I can use my relationship here, let's call it star. We can use star. So from star, we know that dc sed dt is equal to dk d c dt. All right. All I put in is star in here, and then I switch the negative sign to the other side. All right. Okay. So this is our starting place. We're going to say that the change in concentration on the sediment is equal to the change in concentration in the aqueous phase, and this works This is just conservation of mass. But now we need to conserve mass for our REV, all right? So now we need to do this for the REV. So recall that we need this guy to have the units of milligrams solute per liter water. So we can do an analysis here. So this is what we need. We need this unit in order to put this guy into our equation. All right, this equation has liters, change in milligrams per liter water. So we need this reaction here to have that same unit. We need dc sed dt to have the same unit. So we're going to have to do some kind of multiplication of some parameters here to turn this into the same unit. So let's do a unit analysis or dimensional analysis. Let's call this dimensional analysis. Dimensional analysis. All right. So right now, we're starting off here, and we are in milligrams solute per kilogram sediment. And remember, we want to end up here. Okay. So we got to think about how we get there. Well, the first thing we could do is multiply this by kilograms sediment times the volume, or per volume REV. Right, so this is essentially the mass of sediment in our REV. All right, times the volume of REV times the volume of water, or over the volume of water. All right. And if I did this, I would end up with these two volumes of REV would cancel, kilogram sediment would cancel, and I'd end up with milligram sediment times volume of water. All right, so that would give me milligrams solute over V water, which is what we need. All right, and there's a reason why I did this, these two multiplications, because this guy here is the bulk density. All right, kilograms of sediment per volume of REV is the bulk density of the porous media. And volume water over the REV, well, that's just 1 over porosity. All right, so now if I take my C sed and I multiply it by rho B over porosity, all right, I'm going to end up in the right units. So we're going to do it this way. dc dt sorped. And this is an important distinction. This is not the change in sorbed concentration. This is now the change in concentration in the aqueous phase due to sorption. Right? In the correct units, is equal to negative KD rho B over N rho B over N times dc dt. Let me redraw this because that doesn't look good. KD rho B over N times dc dt. Now this is in the correct units and can be put in for R. So a transport equation that considers advection, dispersion, and sorption can now be written by including this term for R. So our transport equation for advection, dispersion, sorption, 1D, steady velocity, can now be written by putting star or double star in for R. So we end up with dc dt is equal to dh d squared c dx squared minus vx dc dx minus kd rho b over n times dc dt. Okay, I'm going to do just a little rearranging here. I'm going to take this term over to this side, combine like terms. All right, we have dc dt in both of these. And so I'm going to end up with 1 plus kd rho b over n times dc dt is equal to dh d squared c dx squared minus vx dc dx. All right, and then one final thing I'm going to do is I'm going to say let 1 plus kd rho b over n equal to rf. All right, and rf we're going to call, and you'll see why, the retardation factor. All right, so we can rewrite this guy now as rf dc dt is equal to dh d squared c dx squared minus vx dc dx. And we will investigate this in sort of greater detail, but the effect of this guy here and the reason why it gets called the retardation factor is that if we were to consider so if we recall the Ogata, if we recall instantaneous step change in concentration for constant (1d) velocity. All right, this is the problem that the Ogata-Banks equation solves. All right, and when you guys have had experience now coding up the Ogata-Banks solution, and if we look at a breakthrough, so here's time. This is the step change to C naught. This is C equals 0. And in white is my breakthrough curve, or actually, let me do it another color. In blue is our breakthrough curve for the case with no sorption, but we have dispersion, so we get this sort of early arrivals and later arrivals. So we have mixing due to dispersion. So this is my no sorption. All right. When I have sorption, what I'll see here, it'll be in the green curve, is that my arrival time, all right, gets delayed as things are sticking to the sediment. All right. And so this delay or retardation is due to sorption. All right. So that's why we call it a retardation factor. It slows the movement of the solute down. All right. It keeps it from moving at the same speed as the fluid velocity. So the effect of sorption is to make solute move slower than the fluid velocity. All right. And that's because there's a sink initially of solute. And then as the solute sort of slowly progresses, that solute can now come off of the sediment. So you end up with a very similar curve, but it is delayed. Okay. All right. So this is our initial foray into considering reactions and the effect of reactions. Sorption being this first really simple reaction, but by even adding this very simple interaction, we see that the transport gets more complicated. We have now solute that isn't moving at the fluid velocity because it's delayed by this reaction. I think I'll end the lecture there today, and then tomorrow we'll start talking about different kinds of reactions in the aqueous phase and how those reactions can get implemented. And we'll consider another very simple aqueous phase reaction, but one that's commonly used in the groundwater transport industry. All right, thanks for your time and hope you have a good day.